Good evening. Welcome to the MyCP webinar for March. I am really excited to have Dr. Zach Vesoulis here to share with us a bit of an overview about artificial intelligence and then how it can be applied to cerebral palsy and then some specifics on some work that he is driving in the network to explore this. So exciting topic. So we're going to go through a quick introduction to the CP Research Network. For those that you attend, usually there's just one bit of new information in there, as well as some updates, so it may be worth paying attention to that. And then I'll hand the microphone and the screen over to Dr. Vesoulis, and then we'll do a Q&A. So I want to remind everybody, March is National CP Awareness Month, culminating in National CP Awareness Day on March 25th. And so if you haven't been bugged by me already, we have our third annual CP Awareness Month contest. We have $1,300 in cash prizes as Amazon gift cards, cash prizes. We have 3 submission categories, and you can submit up to March 15th. We're looking for things that are about holidays and celebration, being out and about, photos that demonstrate diversity of our community. And we'll turn on the voting. We'll close submissions and turn on voting on March 16th and run that for about 6 days. And then we will tabulate the winners. And overall prize is $500 and $100 in each category with sort of a stair step down for first, second, and third place. So if you're interested, sign up and submit. And you can go to cprn.org photo contest. We're really getting some great photos. In fact, here's just a little snapshot of a few photos that we've gotten of the 113 that we've had in the first 18 days of this submission process. So I really love the one with the elf on the shelf. Because it really sort of conveys on. I love them all, but anyway. Okay, so a little bit about the CP Research Network. Our mission is to optimize the lifelong health and wellness of people with CP and their families through a focus of high-quality research, education, and community programs. So since we were founded in 2015, we launched a CP toolkit from diagnosis to understanding to help families with a new diagnosis sort of understand the journey of CP, and we've served more than 5,400 of those. We went on to release a well-being guide and to translate the CP toolkit into both Spanish and Portuguese. And then in the MyCP platform, we enabled web personalization to provide you a lot of that same type of information, but really narrow it down to what's specific for you based on your type of CP. On the research front, we were really founded around the concept of creating a clinical registry. A registry or a database of data about people with CP. That was launched in March of 2016. It is now over 9,500 patients. I expect later this month we will cross the 10,000 mark, which really can power a lot of finding and preliminary data for studies. We also have a community registry, which captures information from you, from your lived experience. That was launched in March of 2019, and that has 2,600 participants in it now. Research CP is our patient-centered research agenda. We've done 2 of these, published one in 2018, and then one about dystonia in 2022, I do believe. And those really drive the sort of prioritization of our research efforts. We've gone on since founding to receive some significant funding milestones from the National Institutes of Health, from the Pediatric Epilepsy Research Foundation, and then more recently we partnered with the largest private funder of CP research, the CP Alliance Research Foundation. We have 31 active studies under development in the network that are somewhere between just a concept that's been approved all the way through to studies that are executing. We now have 5 quality improvement initiatives, 4 of which were launched in the network in 2020. And I just got news of our 13th publication. I'll be doing a blog post about that sometime in the next week or so. We have had over 39 academic presentations, and we've got 5 more manuscripts in writing. So we're really gathering a lot of steam in terms of publishing off of our work. And then on the wellness front, we're partnered with the National Center for Health, Physical Activity, and Disability to really bring the mentor program to adults in the community. So we are a 501c3 that really tries to bring together community members as advocates and people with lived experience, with clinicians, with clinician researchers, therapists, everyone coming together to improve outcomes for people with CP. We have a data coordinating center where our registries or our databases are stored and which we work with to do our biostatistics at the University of Pittsburgh's Epidemiology Data Center. We have both a clinical and community registry stored there, and then we have our education and well-being programs. MyCP, I noticed that 4 of you were not part of that. I'd really encourage you, if you haven't joined it, even there's a place even for clinicians to join and participate in some of our discussions. But for community members, it gives you access to participating in research as well as discussions about research and personalized web information. And you can go to mycp.org to sign up. So just to give you a little bit of an idea about what a registry is, I went to update this today from the latest data. Unfortunately, the patient age data was not correct, so I left in the data that's from 2021, but it'll convey something. So with 9,500 patients in it, you see the distribution of gross motor function classification system. That GMFCS scale is really important for understanding how you move through the community. And it really is important for the way studies get conducted. So you can see we've got very large numbers across all GMFCS levels. And then if you look at age for the clinical registry, you see that it leans to the left, meaning we have more patients that are pediatric than adults. We have about 22% of the people in our clinical registry are adults, and that's because it's people that are going into one of our centers to be seen, and that's where the data is captured. And as you know, there are fewer adult providers that are CP knowledgeable, and so we don't have as many there. If you compare this to the the community registry, you see a very different distribution of GMFCS, and you see an age curve that leans to the right. And so the community registry, instead of having a clinical bias as to who goes to the hospital, it has a online bias. Who's online, who is out advocating for themselves. And so you see that there's much more of a lean towards adults being active online to go out and advocate for themselves and get involved in research. So this is our team to the left. That's a subset of the team when we met in 2019. I probably should update that to our picture from 2023. In the lower right is the group of people that met in Chicago to set our patient-centered research agenda, our educational resources, and then just a nod to our health and well-being program. We are 31 centers now across North America. I actually have to update my green pins because Children's National just joined, and Shirley Ryan Ability Lab, which has been participating for quite some time, just formally joined. So green pins are sites collecting data into the registry. Yellow pins are working on the technology. Red pins are working on getting the compliance agreement done. That red pin's been red for a long time. And the blue pins are sites that have raised their hand and said they want to join the network. So very exciting with the growth of the network. The green circles are the sites that are lifespan. So that's where our adults in the clinical registry come from. So with that introduction, I want to turn it over to Dr. Vesoulis to talk to you about artificial intelligence and cerebral palsy. So take it away, Dr. Vesoulis.
All right, thanks, Paul. Let me switch over and share my screen. Oh. Okay, hopefully everybody can see my screen.
You can.
All right. So yeah, like Paul was saying, I'm going to talk on a topic that's maybe a little bit different than what is normally covered during these webinars, but something that is certainly really hot right now, something you hear a lot about in the news, in medical literature and the lay press, all sorts of different areas. And that's the application of artificial intelligence, which is sometimes called machine learning, and how that can help us with medical research specifically related to CP. First, some disclosures. I'm fortunate to have a lot of different sources of funding that help with all the various projects that we're working on here at WashU and with collaborators. So this is just a short outline of what I was hoping to talk about this evening. I'm going to introduce the idea of artificial intelligence just in general, and some of the basics behind it for those of you that are newer to it. I'm going to talk about how AI is being used right now in the real world, and then also some medical research projects that have been done, and then some that we've worked on as well. There's some really important limitations of AI, at least as it is in the state of the art right now, that's important to keep track of as we move forward and include it in more and more research projects. And then I'm going to talk about one of these projects that we have planned in collaboration with CPRN. So when we think of artificial intelligence, the first thing that comes to mind, especially for those of you that are sci-fi fans, is sci-fi. HAL 9000 from 2001: The Space Odyssey, or the Terminator. With these robots, these things that emulate humans or emulate somebody that you can actually talk to. But that's not really the way AI works in real life. This is actually where it's used the most. Every time we turn on the Weather Channel and get the weather forecast, that's actually AI these days that's behind all these forecasts. I got these figures from NOAA, the federal government meteorologic organization. You can see math is not my forte. That's an awful lot of Greek symbols down at the bottom there that they use to make these calculations. But all of it is to try to predict the future. In the financial world, AI is heavily used in the stock market to try to predict where prices are going to go in the future and when it's the right time to buy a stock or sell a stock. And this is something just from last week that I put in here. Wendy's now is using AI to predict the number of people that are about to go and buy a hamburger, and they're going to change the price. So if they're predicting more people are going to go buy hamburgers, they're going to charge more for hamburgers. So AI is really touching every single part of our daily lives, even if we don't realize that it's happening. So what is it? So really, it's a computer program. That's what it is on the underneath the hood. And it's a computer program that makes predictions. They're constructed in a way that's actually fairly similar to the way that the human brain works. So our brain has a lot of individual nodes. Those are all these circles on the screen here that are all connected to each other through neurons. And as we learn something or figure out a new skill, the connections between these neurons change. Some get stronger, some get weaker. And that's how we learn through practice. Every time we practice singing a song or writing or any one of the various things that we do over the course of the day, every time we're successful with that, we strengthen those connections so that the next time we do that same thing, that pathway is easier. And our brain starts to predict what we want in the future. Machine learning works exactly the same way underneath. Now it seems like magic in the middle there. That's why I've got the wizard, because we don't set these connections. The computer sets these connections themselves. And the way we train, we actually call it training, like the AI is going to school. The way we train it is by giving it tons of examples. We come up with 1,000 pictures of ducks, for example, if we want an AI that can recognize a duck. And every time it sees a duck, then it strengthens those particular connections. But when we're training, we also need to train it on things that are not ducks. So we show it pictures of ducks and turkeys. And so every time it sees a duck, that connection gets stronger. Every time it sees a turkey, it knows that particular connection is wrong. It's not predicting a duck. So it's making both positive and negative connections in the brain or in the computer program. It's the same thing happening in both places. And just like us, the more times we practice, the more examples we see, the better it gets, the more accurate it gets. And the specific details of all of these types of models don't matter. This is just meant to illustrate that there's lots of different ways that AIs are put together underneath. There's not just one system. There are many of them, and people are inventing new ones all the time that are even better or faster or more predictive than the ones that came before. So I started to talk about this a little bit already, how you make an AI system. And so the classic way of doing it is supervised learning. That's what I described already, where you give it a huge library of examples and you tell it, I guess in this case, I decided to call it apples and bananas instead of ducks and turkeys, but it's the same idea though. You give it a very large listing or group or database of information that's already labeled. An expert has gone through, somebody who is really good at telling the difference between apples and bananas and has labeled them all. And given that particular row in the database, that label. And so the AI is trained on that. When we're training it, we typically take some of that database. We don't use all of it to train because we also want to test it. We want to test how good is our AI system. And the standard practice, this is just a convention, there's not necessarily science or math behind it, is that we take about 80% of our training database and use that to learn. And then we save another 20% of it to test it later. So this is like math class in elementary school where your teacher comes up with 100 problems and you practice 80 of them, and then they save 20 of them for the test. So that's exactly what's going on here. And as we develop the model, we keep testing it over time and we make adjustments to it, and then we test it some more, trying to make it more and more and more accurate. Now, this is all supervised learning, which is very familiar to us because it's like I said, that's how we as people learn. But AIs can also do something called unsupervised learning, which is a little bit related to something that humans do. But this is where you give it a data set, but you don't label it. You give it a bunch of pictures of fruit, but you don't tell it what an apple or a banana even is, and you leave it up to the AI to group it on its own. It looks at all of them and it decides, all of these things are yellow and kind of curved shape. I don't know what that is, but they're definitely in one group. And all these things are round and red, so they belong together too. That's called unsupervised. And when you start doing unsupervised machine learning or AI, surprising and unexpected things happen. We as people, particularly from a medical perspective, all come to these sorts of problem solving with biases. And it's based on our experience, what we learned in medical school and our training. And so many of the computer programs we come up with basically are robotic versions of us. They do the same things we do. They think the same way that we do, which is good because it can perhaps help us be better at our jobs or be faster at our jobs, but it's not different. Computers can take that to the next level. They can find surprising relationships that we never would have thought of. It's a form of creativity in a sense that the computer can accomplish that we're somewhat blind to because that's not how we were trained. Now, AI is increasing exponentially in terms of its capabilities, particularly I put here 10 years, really in the last 2 years, it's rapidly accelerated. Supervised learning was really the state of the art until about 2017. Self-supervised learning or unsupervised learning, which I was describing, is much more recent and is really the state of the art. If you've heard of ChatGPT, which you hear people talk about sometimes, that's all self-supervised learning. That's how those algorithms are working underneath. And not surprisingly, it's been applied to medicine. These are just 3 different examples of papers where AI algorithms have been developed that either replicate what a human is already doing, a human doctor is already doing, or even expand upon it. So one of them is looking for those people that have diabetes, have screening regularly for retinopathy, for eye problems related to their diabetes. And AI, if you take pictures of the back of the eyeball and feed it into this algorithm, it can do this screening for you. You don't need an ophthalmologist to do it. The computer can do it. The same thing is true with photographs of skin cancer. You can give those to an AI and it can tell you whether that's skin cancer or not, whether it needs to be biopsied or not. And then there's also a lot of different algorithms out there that look at radiology, that look at X-rays and MRIs and try to find the pneumonia, for example, on the MRI, on the chest X-ray. This is a nice slide showing how many different algorithms are not just being developed, but are going even further. These are all FDA approved. So these are so good that they've met the very stringent bar that the FDA has for AI for use in clinical practice. And there's a lot of them. And this particular chart stops in 2020. So you can imagine how many more there are even since this was published. The NICU. So I'm a neonatologist, so I spend my time in the NICU. So that's where my thinking usually is, my thinking cap. And it's a place where there's a huge amount of data. AI works the best when it's working on lots of data. This is just a sample picture of what a NICU bedside looks like. And you can see all the machines, and each one of these machines is producing data, all of which we can link back to a database like CPRN, for example, or related or correlated databases, and we can use it to learn what's happening to that baby. We can feed it into these algorithms, either with labels or without labels, to have it identify patterns that can predict problems before they occur and potentially within a window where an intervention can be made to change the course of the baby that we're taking care of. But like I said earlier, we have to be really careful about how these systems work. So AI is very, very, very good at finding patterns, but it's a computer at the end of the day. It doesn't know what any of the things it's looking at mean. So my example earlier from apples and bananas, it can tell you, especially a well-trained algorithm can tell you with 100% accuracy whether something is an apple or a banana, but it has no idea what an apple or a banana even are or what fruit is. It's just a picture to the computer. So these are some examples from a really nice project that was done. This was an AI algorithm that looks for two things. It can look for cardiomegaly, so that's when there's an enlarged heart, and it can find pneumonia on a chest X-ray. So you can see in both of these panels here, the one on the right is the X-ray, the original X-ray that was taken in the hospital. And in the picture on the left is the AI algorithm that's an overlay on top of it. And those numbers are supposed to represent where it's predicting what the problem is. So it predicts so a higher number means more likely related to that problem. So in the top left here, you can see all the yellow is right on top of the heart. That's what's right in the center of the chest X-ray. So those numbers are higher, and they should be because that's where the heart is. But you can also see, and I circled them in red here, that there's two other areas that are higher than expected, much higher than the background. And so the one on the top right says portable. So that means this is a portable X-ray. It was taken on a machine on wheels, and those are generally taken on patients in the ICU. If somebody's not in the ICU, they go down to the regular radiology floor and they do one with them standing or sitting up instead of laying flat like they would on a portable scan. So the AI algorithm has recognized that somebody is more likely to have heart problems if they're admitted to an ICU. Not anything to do with the heart at all. Just the fact that they're having a portable X-ray taken is a sign that that patient is probably sick. There's also, you can see it goes up with that little L right there. Those are markers that the X-ray techs put on that show the left and the right side. This is an L here because that's the left side of the patient. That particular marker type is used by portable X-ray techs, which looks very different than the markers that are used by the X-ray techs down in radiology. So again, the algorithm is learning these accessory things on the screen that have nothing to do with the diagnosis at all. This pneumonia example is very similar. This X-ray does not have pneumonia on it at all. But what it does have, that thing that's circled right there, is an electrode. So this is a patient who has heart monitors on that's measuring the heart rate. And again, those go on patients that are sicker. So it is recognizing sicker patients because of the monitoring devices that are attached to them, not because of anything to do with the pneumonia at all. So again, this goes back to that same issue that the machine learning algorithm doesn't know what any of the stuff means. It's just looking for patterns. So I'm going to give one quick example, and I'm trying to be respectful of everybody's time and speak fast here, but not too fast, of an AI project that we did that we published last year. And this is a hybrid human AI example. So we developed a scoring system for brain MRIs for babies with hypoxic ischemic encephalopathy or birth asphyxia back in 2017. And it's a really complicated system. It's got lots of different parts. It looks at both sides of the brain and a lot of different sequences, a lot of really technical MRI stuff. And at the end of the day, you can see it's in red here. There's 81 different elements. That means the radiologist, when they're looking through the MRI and trying to score it with the system, needs to look and write down a score for 81 different things. As you can imagine, this only gets used in research. Nobody uses this clinically. It's just too slow. It takes too much time. Um, so I suspected that we had too much in this system already, that some of the things that were in there were overlapping with each other. Some of them probably were not important at all. And so we used AI to help us find the parts of the MRI score that were helpful for predicting outcomes. So in this particular case, we looked at motor outcomes. So we were looking at those who had less than the 10th percentile on AIMS, so the Alberta Infant Motor Scale, or the motor component of the Bailey-3. Those are two different neurodevelopmental tests that were done at 12 or 24 months. So we put it into a AI system, and you can see in this table right here, we built a lot of different systems. Each one of these rows is a different kind of AI. And the one in the first row is the absolute simplest kind. That was what was in our original paper from 2017. And the one at the bottom here is the brand new one that we came up with this. And we can see we've doubled the accuracy. Even without figuring out all the details of the math here, you can see the accuracy is twice what it was before, and the precision is 3 times. So I put these little figures on the right here just to get home the concept of precision and accuracy. So precision is where all of your guesses, if you're guessing multiple times, are close together. It doesn't necessarily mean that you're right on the bullseye, but it means at least all of your guesses are the same. So in this upper left example, that's high precision but low accuracy. They're all the same shot, but they're not anywhere close to the bullseye. Down here on the left, there's low precision and low accuracy. They're not the same, and they're not anywhere near the bullseye. The high accuracy but low precision is all right around the bullseye, but not on it. And what we really want is this one. We want both of those numbers to be high. And so as we got to more and more advanced AI systems, we got higher and higher precision and accuracy out of these tests. The other thing that we looked at is the AUC, or the area under the receiver operating curve, which is a really long way of talking about how good this classification task was. How good were we with our system at predicting which babies were going to develop motor problems in the long run. And so the number closer to 1 is definitely what you want. And it literally, so this is the curve right here, it literally is the area under that curve. If you shade it in and measure the area, that's what we're talking about here. So you want something closer and closer to 1. So what we wound up finding in the end is not only was our system more accurate, but instead of having 81 parts, it had 3. And we doubled the accuracy and tripled the precision by using only 3 instead of 81. But we picked, using the help of the AI, the best 3 things to do that. Oops. So the way this connects to a future project. So this, of course, is the background for something Paul and I are planning for the near future. So we know right now MRI practices are very variable between individual hospitals and universities. Some places use very little imaging, some use a ton of imaging, some have these risk-based strategies. And right now, even regardless of the reason why somebody orders an MRI, it's done. A radiologist looks at it. They don't use a system like I described. They just look at it and they write down their subjective interpretation of what they see on the MRI. And then that report gets sent to the patient's doctor. And then that doctor reads what they wrote, and then they provide their own interpretation of it, which is what they share with the patient or the family. So it's actually gone through 2 different subjective reinterpretations before it ever gets to the patient, which is definitely not the best way to communicate information. You can imagine that there's a lot of chance for information to be lost through each. It's a game of telephone, essentially, between each of these steps. And it also depends on the skill and experience of the people reading the MRIs. There's a whole lot of different research that we can do with MRIs. I have 2 very pretty pictures on the left here showing some very sophisticated MRI research. Volumetric analysis, where we can actually shade different parts of the brain in different colors and then calculate the volume to look at how well different parts of the brain are growing. We can do something called diffusion tractography. That's the second from the left rather. And that's using MRI to measure fiber tracks. All of those connections between different parts of the brain can be isolated, and we can see how different parts of the brain connect to each other there. The problem is at least the current state-of-the-art tools to do these require very, very high bar of MRI to go into those systems for it to work. Some of that is technical, and some of that is just because of the people that have developed these tools are very stringent with them. They'd want the best MRIs to go in there, and they generally don't tolerate ones with artifact, which I've shown on the right here. One is called ringing artifact, so you can see almost like a bell that has been rung that's shaking. That's from patient movement, and then there's also these are just two examples. There's lots of other kinds of artifact that show up in MRI. This is called a zebra artifact. So these MRIs are interleaved, so it's doing every other row when it's capturing the signal, and this patient has moved between the two of them. So that's why it looks like zebra stripes, because the head is in one spot on one row and in a different spot on the other row, and it goes back and forth between the two rows. So the idea that we're working on in this project is to try to figure out a way to correct the problems in these quote unquote clinical grade MRIs and make them research grade so that many, many more MRIs can be used for research. Like Paul was talking about at the beginning, it's almost 10,000 patients in the registry, which is way bigger than any research study would ever be able to be. The NIH would start crying if we told them we wanted to do 10,000 MRIs, because it's just so much data. But if those MRIs are already being done, they should be used to learn new things and to discover new ways of looking at CP. So there's a couple different motivations here. So one I've already talked about, that these research grade tools shouldn't be limited just to tertiary referral NICUs for patients in research studies. That's just far too little access for far too many people. Second, there's a lot more information. Like we talked about earlier, these algorithms can see things that we can't with our eyes. So there's a lot more information in there than we can ever perceive. And so we can use AI to do these tasks. So we can use it to remove artifact, to make research grade images out of clinical grade MRIs. And we can use it to detect these novel imaging features, which is sort of a term of the art, to describe just different findings, different ways of looking at the MRI to come up with a prediction of an outcome. And so we think that this can be used to achieve better prediction of, just as one example of a research question we can answer, better prediction of ambulatory outcomes like the GMFCS that's on par with a neurologic exam or perhaps even better. And it can be far more reproducible because it's a computer. It's going to give you the same result every single time, even if it hasn't had a cup of coffee yet. So there's a lot of different things we can do. So the first, like I've talked about, is artifact correction and reconstruction. This can help because it reduces the need to rescan patients. Oftentimes there's too much motion and somebody needs to go to an MRI again, and it's a big deal to go through an MRI. So if we can reduce the number of unnecessary MRI repeats, that's great. It makes better quality images for the radiologist to read, and like I said, expands that universe of imaging that we can use in research. We can try to create a robotic radiologist through AI tools. We can train them on labeled scans, and that's much better inter-rater reliability. So it doesn't matter who happens to be reading MRIs the day that you or your child gets an MRI, the computer is going to give the same answer every time, and it's also faster. It's an excruciating wait when somebody gets an MRI and it's a Friday and they have to wait all the way until Monday to get a result. That we can try to avoid that kind of problem. And it also expands the scope of facilities. Some sites could have an MRI scanner without having a neuroradiologist at all. And these can be sent electronically to the computer algorithm where it gets scored. And then, of course, the most exciting thing from a research perspective is to do discovery, to use these tools to discover new things about the development and progression of CP, so that if we understand those mechanics, then that helps inform interventions that we can then push backwards in time and have a direct impact. So I think I've already said all these things in the conclusion here, so I'm not going to repeat myself again. But with that, I'd like to thank, there's a ton of folks at WashU that are a part of all of these projects, of course, all the different sources of support and collaborators, not the least of which is Paul and the CPRN. And with that, I'd be happy to take any questions anybody has.
Great, thanks. That was great, Dr. Vesoulis. Thank you so much. And I really am, this was an idea I've been trying to find a partner on for about 6 years. So I'm really excited that you have so much interest in this. Would you mind turning off your slide share just so we can have a bigger screen of people? And Jay, go ahead. You're first up with the question.
Yeah, hi. Can you hear me okay?
Mhm.
Yeah.
Yep.
Okay, great. Yeah, so I actually study AI in my PhD program right now. So I'm actually interested in some of the technical details, if you could provide those for this proposed research in terms of what approaches or models will be used.
That's a good question. We don't necessarily, we haven't quite landed on what the final strategy is going to be. It probably is going to be a combination of different tools. There's some of it, the image reconstruction. There are existing pipelines or platforms out there that do some image reconstruction, not in the neonatal brain or really even the pediatric brain. They're more designed for adult MRIs, but certainly are a great starting point to work on improving that image quality and reconstruction. Some of the research tools that are out there, things like the tractography or the volumetric analysis, those already exist. Those are things that we use in research now. But it's a matter of connecting this large pool of MRIs through image refinement before we can load them into those pipelines. And that's more conventional. And then for learning, there are a lot of different partially trained image classifiers that are out there. And I think some of it is probably going to depend on, which ones have the best performance. I don't think there's any off-the-shelf things that we're going to necessarily be able to use without modification. Everything's probably going to require at least some modification, if not some novel new pipelines in and of itself.
Okay, great, thanks. And are you able to provide a reference to the published work that was discussed in the talk? I didn't
Yeah.
see one in the slides, but
Yes. While we keep talking, I'll put it in the chat. I'll paste a link to it in the chat.
Great.
thanks.
Questions. Other questions? Go ahead, Poonam.
So I was, and I'm sorry if this sounds very naive, but I was wondering, once you develop this, you go through this research and kind of get a handle on how it works, then how can that be applied to adults who have CP and see, okay, what kind of backtracking that now we know that the adults, they have this GMFCS and what their MRI kind of looks like is what you predicted.
Yeah. That's if I'm understanding your question correctly, I think that's exactly it. It would be really valuable, I think, from a understanding perspective, if there's somebody through the course of childhood and then into adulthood has had MRIs over that time period, when they're a baby, when they're school age, when they're 5, when they're a teenager, and then when they're an adult, and apply these pipelines to look at things like connectivity and to look at the change in volume of different parts of the brain over that time span to see how the brain grows and changes and develops, and is potentially impacted by cerebral palsy. And then we can also look at that with people that have different life experiences too. Some who have better access to therapy and assistive devices and all the supportive technology they need, and then perhaps some people that don't, and see how that affects the plasticity of the brain as well. There are many different types of questions that could be asked, particularly with longitudinal data like that.
So if they haven't had MRIs in childhood, but now they're adults, is there a way to kind of relate anything?
So on an individual level right away, perhaps not, just from a single person. One thing that AI algorithms are very good at, that's sort of typical or conventional statistical tests are not, is they're very good with missing data. So if the group or pool of patients that are in the system have MRIs at different times and different numbers of MRIs. The AI doesn't care about that. It takes the data that it has and it can fill in the gaps in between. So you can use AI in that sense to make guesses about what things were like 5 years earlier or 10 years earlier, once it's had enough time to learn from many other similar people in the past.
The other
Thank
thing,
you.
the other thing I would add is just as we get more data sets to apply. So let's say you participate in a genetics study, and so we've got genetics data, and then you're participating in MyCP, and we have all this lived experience data, and just all these data sets can be sort of thrown at the model for it to figure out the patterns and make associations that are just far too complex for your average human to sort of string together, or a really good biostatistician, because it's just so much data. Susan, you ready to ask your question? So you got away there for a second, but go ahead.
There it goes. Thank you. My best friend and I both have cerebral palsy, and I was born 2 months premature, and my best friend was born 3 months premature, but she's less disabled than I am. And I was wondering if any of the research you're doing accounts for things like that. Thank you.
Yes. Oh, absolutely. And that's what a great comment and a lived example of one of the most humbling parts of neonatology. Right now, with the kind of information that we have and the types of tools we have, how not good we are at predicting the future. We can make guesses, rough guesses, and often the thing that we use is things like how early a baby was born. There certainly is some correlation, but like you've shown very, very well, it's not perfect by any means. We as we get more data and we use computers to help us process these data, we're I think going to start to make more connections. We will understand why two babies, and I see this in my everyday life, two babies that have very similar starts in life and very different outcomes. And I've seen that not necessarily just with two friends. I've even seen that the best example I can think of is a set of triplets I took care of quite a few years ago now, almost 10 years ago now. All three of them had very different outcomes, and they're related to each other. They're triplets, and they were all born to the same mom and the same dad at the same hospital, taking care of the same doctors, and had very different outcomes. So it's right now, the true answer to those questions, I think, is beyond our ability to give you. But it's certainly something that we want to do someday.
Great answer. Thank you.
Huh?
Okay, I'm worried that I'll mess up your name, but for Feruza, you're up.
Yes, it's great to meet everybody, and I have a question maybe a bit different from what Zachary was saying, because we have built and trained the neural network in slightly different area.
Mhm.
We are building we trained the neural network to interpret oral motor apparatus
Mhm.
and fine motoric. Basically, the idea was to do the speech therapy exercises, particular oral motor and fine motoric for wrist and finger and sounds as well. And
Mhm.
we were piloting the app in a boarding school for kids with cerebral palsy.
Mhm.
And seeing some great results. So maybe my question is more to Paul, because we definitely want to adapt the app for kids and adults with cerebral palsy. What is the best way to show the app and maybe discuss what data is needed to increase accuracy and precision? The current range is 75 to 95%. And it's not that simple as Zachary was mentioning, because we're interactive. And we were accelerated by CIMET So we currently operate as wellness app, but we are moving towards the medical device class 2A. So what's the best way to cooperate with you guys? Or
So I am going to put into the chat 2 contacts. Mine and Christy Bjornson, who's our scientific director. She was on the call earlier. So for a research collaboration, Christy is the right person to reach out to, so giving you her email. And if it's more about, exposure, if it's not about a research project, but it's about sort of partnership to get exposure, that's best sent to me for now. So,
thank you.
okay. Chris, go ahead, you're up.
Yes, good evening, everybody. My question for Zachary, is an MRI, with what you guys are doing with AI and everything, could that be used to see where you are in terms of being an adult with cerebral palsy? You mentioned earlier that sometimes when you're, when you have kids or, or what you're usually with and everything, I'm just wondering if there was a way to see where, say, for example, I am in my cerebral palsy, even though I have mild cerebral palsy, and I just want to see what part of my, my brain that is, or whatever it is, that makes why my brain has why I have the cerebral palsy. I was just wondering if that would show patterns or anything.
Yeah. I think that's a great question, and that's I'm a neonatologist, so I'm always thinking about babies. But you're absolutely right, though. The types of tools and strategies that we're talking about developing can work on any population. We're going to start with babies, but there's absolutely nothing stopping a future version of this from being with adults. It takes exactly the same approach, that we would need a large enough pool of adults with CP where we have an MRI and we have information about their CP for it to learn from, and then we can start applying it to people to make predictions for individuals.
And I would add to that, Chris. So when I talked about being interested in this project for trying to find a collaborator for 6 years, a big portion of it is, people get this diagnosis, at some relatively early age for the parent, for the child. And it's really hard to understand what the sort of removal of the layers of the onion will be and how different it is. So one of our sites, Cincinnati Children's, gives parents what's called a care map. And it describes what milestones and what interventions might happen over time for sort of the early years. But really what I want to get to with all this data is something that, think of it as like Google Maps. And, you got the blue dot, and that's where you are. And there's like minor roads and major roads about where you can go, and there are lots of off ramps and whatnot, but trying to be able to bring that level of sort of visualization and prediction to getting to different places and understanding where you are relative to the rest of the population. So that really fits a lot with the sort of vision, but this is a building block that we're talking about, but it's an exciting one. So go ahead, Paul.
Yeah, so just to dovetail on that a little bit. So as you know, AI is we don't know what we don't know as far as where it's gonna lead to. So it seems like, and I don't want to oversimplify, but it seems like what we're doing right now, this phase, is kind of cleaning up the data and normalizing the data. Is there some future thought as to doing some unsupervised learning, letting the machine learning just figure out stuff on its own?
Yes, absolutely. Oh, I'm sorry. Go ahead.
No, that was it. You got it.
Yes, that is, you're absolutely right. the first step is really to clean the data, to get it as good as we can, so that we can move on to those next steps. So step one is really clean it up and make it the best we can. Number two is to use everything in the existing pipelines and strategies that we've already developed. And then the third, and I think the most exciting, is just what you described. Put it into those unsupervised algorithms to see what we can discover, to find new connections, relationships between the way the brain appears on the MRI that humans may never have come up with on their own. You know, it might be this little spot in this one part of one sequence is connected to another little spot in a completely different part of the brain on another sequence, and it never occurred to anybody to connect those two things together.
Well, and then we correlated with some other data base out there, and it's like, okay, well, yeah, there was this other circumstance and the contributing factor.
Yeah. Yeah, we didn't, I didn't show this example because there wasn't time in the slideshow, but there's another project that I'm working on with some colleagues from Boston and San Francisco, where we look at neurodevelopmental outcomes of children with heart disease, congenital heart disease. And we use AI to try to predict which things are going to influence their outcome. And it can find just one example of these sort of novel ways of looking at things. We expected things like maternal education or income, those might be influencing factors, but what was actually the most important thing was the age of the mom. When we looked under the hood at it, it's not a linear relationship. For most ages of mothers, the age actually doesn't matter. It has almost no difference on prediction of good or bad outcomes. But when the age is really young, a mom that's less than 19, or a mom, the outcomes are far worse. And when a mom is much older, when a mom is over 35 when the baby is born, the outcomes are much better. And it turns out, even though we're piecing these things apart, we're talking about the income and the education level and their zip code and all those sorts of things, that it's really just the age. And if you are having children at an older age, you're old enough to have gone through your education, and you're old enough to have a stable job and stable housing. And that is a far more important predictor than any one of those individual pieces in and of itself. And that's an idea that we had thought of, but never really put together in that particular way. So I think these are the exciting ways that AI can make us even rethink ideas we already have in a new way that's different.
Let me cap that by saying this, that the grant that Dr. Vesoulis is working on for NIH envisions not only doing that cleaning, those other things that he talked about. You know, we need to not be too grandiose in what we're going to think we can predict, but we're going to work towards that, so that we will do the cleaning and the unsupervised analysis to try to get those predictions, and that'll be a stepping stone to so many more things where we can go from maybe, you know, unlabeled MRIs and this rich registry to predict all sorts of outcomes that are found in the registry or comorbidities that are found in the registry from the MRIs. Somewhere down the road, we'll add genetics. Just the possibilities are large, if not endless. So I want to wrap there. I really appreciate everyone's engagement. Dr. Vesoulis, thank you so much for your time building a presentation that was you know, educational and lay friendly. I greatly appreciate that. I think this will live on as a great resource for people wanting to understand this. So thank you all very much. Thank you, Dr. Vesoulis. I will see you tomorrow morning, bright and early. Anyway, thanks everyone. Good evening.
Bye.